Hi, in this video I'm going to talk about the complex exponential function, or in signal theory it is named as the complex exponential signal, which is a very important signal type since it is used in the representation of arbitrary signals in terms of a superposition of complex exponential signals. So the complex exponential signal is like a building block in signal theory. Now, in order to start, let us remember the concept of periodicity, what we mean by a periodic signal, because periodicity will play an important role in the representation of complex exponential signals. So a signal x of t is periodic if x of t is equal to x of t plus capital T for all t. So this equality tells us that the signal is periodic with a period capital T. So x of t is periodic with period capital T, where t is taken as a positive constant. For example, cosine t is periodic with a period equal to 2 pi. So cosine t is equal to cosine t plus 2 pi. But the period is not unique because cosine t plus 2 pi or cosine t is also equal to cosine t plus 4 pi as well. Okay? And in general, we can write this as cosine t plus 4 pi, or rather 2 pi k, where k is an integer. Now it can take positive values or negative values, but for positive values, remember we have defined the period as a positive constant. Any integer multiple, positive integer multiple of 2 pi is a period. So the smallest value of the period is called the fundamental period. So 2 pi, 4 pi, 6 pi, etc. are periods, but 2 pi is the fundamental period. Fundamental period, and it is denoted by T0. Okay? So the smallest period is called the fundamental period. Similarly, x of t equal to sine t is also periodic with the fundamental period again equal to 2 pi, but 2 pi, 4 pi, 6 pi are all periods. Okay, so here I'm just going to write down the fundamental period, which is equal to 2 pi. Now, if we write down the following signal, for example, x of t equal to cosine omega t. Now this symbol here is the Greek letter omega representing the angular frequency. Okay, omega is angular frequency given in terms of radians per second. Now note that the argument of the cosine function is measured in terms of, is an angle, therefore it's measured in terms of radians. So here we have the product of omega with t measured in terms of radians, and t is in terms of seconds, therefore omega has the unit radians per second. Now in this case, the fundamental period of x of t, t0, will be 2 pi over omega. If you wish, let us call this omega 0 to denote that it is a constant. So omega 0 is the angular frequency of the cosine signal, and the fundamental period t0, this is the fundamental period, is equal to 2 pi over omega 0. Now, similarly, we can define again as x of t sine omega 0 t. Okay, and it is clear that again t0 equal to 2 pi over omega 0 is the fundamental period of sine omega 0 t. Now, we have these two important signals, which are sinusoidal signals, the cosine signal and the sine signal. Now, the complex exponential signal is obtained as a complex superposition of these two real-valued signals as follows. Now, we are going to call this again x of t, and it will be called the complex exponential, complex exponential signal. And we are going to define it as follows. So by definition, this is equal to cosine omega 0 t plus sine omega 0 t, but sine omega 0 t is multiplied by j. What is this j? J is the imaginary unit square root of -1. Okay? So we have defined a complex valued signal with real part equal to cosine omega 0 t and the imaginary part equal to sine omega 0 t. And we obtain as a superposition cosine omega 0 t plus j times sine omega 0 t. Now, how do we have a shorter representation for this new signal, which we name as the complex exponential signal? Now, in order to obtain this shorter expression, we have to remember certain facts about the complex numbers in general, their representations, the complex plane, etc. Such concepts are essential to continue. Now, remember that if you have the complex plane. This is the real axis, and this is the imaginary axis of the complex plane. A complex number is represented by z in terms of the component along the real axis, which is x, and the component along the imaginary axis, which is equal to jy. Okay, so z is equal to x plus jy, or z equal to x plus jy is the so-called Cartesian representation of the complex number z. Okay, now if we look at the complex plane and this particular complex number z, now this complex number z is represented by this length from the origin to that point, and also by means of the angle between this line and the x-axis or real axis, which is given by theta. And the length of this line is given or shown by r. And it is clear that x is equal to r cosine theta and y is equal to r sine theta. So z can be written as r cosine theta plus j sine theta. Now, if we look at this term here, cosine theta plus j sine theta, now cosine theta can be expressed in terms of its Taylor series expansion around 0 as 1 minus theta square over 2 factorial plus theta to the power 4 divided by 4 factorial, etc. And sine theta is represented as theta minus theta cubed divided by 3 factorial plus theta to the power 5 divided by 5 factorial, etc. Now, what happens if we combine them? Okay, when we combine them as sine theta plus, cosine theta plus j sine theta, it is 1 minus theta squared divided by 2 factorial plus theta to the power 4 divided by 4 factorial and so on, plus j times theta minus theta cubed divided by 3 factorial theta to the power 5 divided by 5 factorial and so on. This can be written as 1 minus or rather plus j theta minus theta square over 2 factorial minus j times theta cubed over 3 factorial plus theta to the power 4 divided by 4 factorial plus j times theta to the power 5 divided by 5 factorial and the other higher order terms. Okay, now it is clear that this term together with this minus sign can be written as j times theta squared divided by 2 factorial. Because j squared is equal to minus 1. And this term, as you see, can be written as j theta to the power 3 divided by 3 factorial, because j cubed is minus j. And similarly, this term is j theta to the power 4 divided by 4 factorial, and this is j theta to the power 5 divided by 5 factorial. Therefore, this is equal to k running from 0 to infinity. So it is a series representation given by j theta to the power k divided by k factorial. Now, this is nothing but the representation of the exponential function e to j theta. Okay, therefore, cosine theta, we have shown that cosine theta plus j times sine theta is just e to j theta. This is one of the most famous expressions in mathematics, known as Euler's formula. And it links the complex exponential function with the sinusoidal functions. Okay. Therefore, the complex number x plus jy is equal to r cosine theta, which is x, plus j times r sine theta is y. But now we know that this expression here is nothing but e to j theta. So we have two different representations for the complex number z, the Cartesian representation and the polar representation. It's called the polar representation because r is just the square root of x squared plus y squared, and theta is the angle which is tangent inverse y divided by x. Okay. So we have these two different representations for the complex number: the Cartesian representation given in terms of the real part and imaginary part, and the polar representation given in terms of the magnitude of the complex number, which is also called the modulus of z, and which is also represented as magnitude of c, and the angle, which is called the argument, is tangent inverse y over x, or it is the angle between the line representing the complex number and the horizontal axis, which is the real axis. Now, after all this discussion, we are ready to look at the complex exponential signal. Now, instead of a constant c, we write the signal x of t, which is the complex exponential signal, function or signal, as the signal whose whose real part is cosine omega 0 t, and the imaginary part is sine omega 0 t. Okay. Now, therefore, for any value of t, x of t is a complex number given by cosine omega 0 t and sine omega 0 t as the real part and imaginary part of that complex number. And by using Euler's formula, we can write this as e to j omega 0 t. Okay. Now, it is clear that x of t is periodic. Periodic with period or fundamental period, with fundamental period t0 equal to 2 pi over omega 0. Now, how can we visualize this signal? Now, let us go back to the complex plane, but before that, we note something. As you see, magnitude or modulus of x of t is 1, because it is the square root of cosine square omega 0 t plus sine square omega 0 t, and this term here is 1, and square root of 1 is equal to 1. Therefore, if we plot the values of x of t for different values of t, this is the complex plane, the real and imaginary axis, the values of x of t will be on the unit circle centered at the origin and radius equal to 1. So this is the unit circle with a center located at the origin and radius equal to 1. Now, as you see, when t takes different values, for instance, let us start with t equal to 0, so at omega 0 t equal to 0 or t equal to 0, we will be at this point. And then here, for which value of omega 0 t, when omega 0 t is equal to pi over 2. So we are traversing the circle in the counterclockwise direction. And this point is omega 0 t equal to pi. And for example, here is omega 0 t equal to 3 pi over 2. And then when omega 0 t is equal to 2 pi, we will be back at the same point, and that's why the period is, or the fundamental period is 2 pi over omega 0. Okay, so this is the visualization of the complex exponential signal on the complex plane. So if we just summarize, the complex exponential signal is a complex valued signal whose real part is a cosine signal and the imaginary part is a sine signal. And the visualization on the complex plane is as follows. We note that the modulus of x of t, or magnitude of x of t, is always equal to 1. Therefore, all the values of x of t will be located on the unit circle. But for different values of t, we see that as t increases, for example, starting from 0, we are going to traverse the unit circle in the counterclockwise direction. And because of the periodicity of the signal, we will arrive at the same point. Okay, for the time instant omega 0 t equal to 2 pi. Okay. Okay, now if we just summarize once more, x of t equal to e to j omega 0 t is the complex exponential signal, where omega 0 is called the angular frequency in radians per second. And t0 equal to 2 pi over omega 0 is the fundamental period of this periodic signal x of t. Now, let us look at the following signal. I'm going to denote it by x bar of t, which is equal to e to minus j omega 0 t. Now, we attribute that minus sign to the frequency. So we have the negative frequency concept. Okay, now what do we mean by the negative frequency? First of all, let us compare x of t and x bar of t. X of t is cosine omega 0 t plus j sine omega 0 t, and x bar of t is cosine minus omega 0 t plus j sine minus omega 0 t. Now, cosine minus omega 0 t is cosine omega 0 t once more. And sine minus omega 0 t is minus sine omega 0 t. So we have minus j sine omega 0 t. So we have an interesting relationship between x of t and x bar of t. x bar of t is just the complex conjugate of x of t. So x bar of t is complex conjugate of x of t. Now let us remember the visualization of the complex exponential signal on the complex plane. Now if we have x of t takes values on the unit circle. So this is the real axis and this is the imaginary axis. So it traverses the unit circle, the circle with radius 1, with center at the origin. So the values of x of t will be on this circle. So x of t will be, the values of x of t will be those points on this circle traversed in the counterclockwise direction. Whereas if we look at the complex exponential signal with the negative frequency omega 0, again this is our real axis, this is our imaginary axis, so we have the representation on the complex plane. Again, if you look at the magnitude of x bar of t, it is again 1. Because real part is cosine and imaginary part is minus sine, so their squares will add up to 1 and the magnitude will be 1. Now we are on the x bar of t will take values on the unit circle. However, the unit circle will be traversed in the clockwise direction. For example, this is the case for the conjugate or negative frequency. So this is e to j omega 0 t, and this is e to minus j omega 0 t, the visualization on the complex plane. So at omega 0 t equal to 0, we are at this point. Then at omega 0, when omega 0 t is equal to minus pi over 2, we will come to this point. Okay. And so on. We are going to traverse the unit circle in the clockwise direction. Now, the negative frequency concept is quite important in the representation of real valued signals, because we will see that for real valued signals, for the representation of real valued signals, we need the negative frequency concept. You can see this fact from this particular example when we note that if we add x of t and x bar of t, we get 2 cosine omega 0 t. So cosine omega 0 t is simply e to j omega 0 t plus e to minus j omega 0 t divided by 2. Therefore, the real valued signal cosine omega 0 t has two frequency components, omega 0 and minus omega 0. Now remember that at the beginning I have told that the complex exponential signal is the building block in signal theory. We use it to represent arbitrary signals in terms of superpositions of complex exponential signals. So this is the simple case where the cosine signal, the real valued cosine signal, is represented in terms of e to j omega 0 t and e to minus j omega 0 t as a superposition. The coefficients are 1 over 2 and the frequency components are located at omega 0 and minus omega 0. Similarly, x of t minus x bar of t is 2j sine omega 0 t, which means that sine omega 0 t is also a superposition of e to j omega 0 t and e to minus j omega 0 t. However, the coefficients are now complex valued, 1 over 2j for e to j omega 0 t and minus 1 over 2j for e to minus j omega 0 t. Okay, we can stop at this point and leave some other detailed discussions to the coming videos. Okay, thanks.